Hello, my name is Jerry Lowe. I'm the head of technology for the advertising and marketing industry at AWS. Welcome to reInvent and welcome to the AdTech track. The star of the show today is the Trade Desk, who is here to talk about how they process over 800 billion ad requests per day. Yes, that is billion with a big B. 11 million queries at peak, all done with an average response time of less than 20 milliseconds. Truly outstanding. Another star in the session is Aerospike, and I want to share a couple of announcements related to them. First, today we are excited to announce our expanded partnership with Aerospike, which is now available as a fully managed service on the AWS Marketplace. Please check it out. In addition, I'm also excited to announce that AWS and Aerospike is collaborating to develop Aerospike compatibility with ARM-based chips. That is for the Graviton 2 instance family. We believe this will improve the cost performance for AWS Aerospike workloads even further. Please stay tuned on that also. Last but not least, compute is the other star in today's presentation. I'm especially excited for customers to hear how the Trade Desk was able to choose the right Amazon EC2 instance types to achieve performance and cost efficiency across their diverse Aerospike workloads. Speaking of compute, we have to talk a little about the Graviton 2 instance family that launched last year. In case you aren't familiar, the results for this processor is truly outstanding. For example, for Nginx, M6G instances average 54% higher throughput at 20% lower cost versus M5 instances. I highly recommend that you take a closer look at the Graviton 2 family. With that in mind, please welcome Matt Cochran, Director of Engineering at the Trade Desk, to talk about their experience with Aerospike on AWS. Welcome, Matt.
Hi, my name is Matt Cochran. I'm with the Trade Desk. I'm Director of Engineering for our data engineering team. We cover a lot of high volume applications as well as machine learning and in other technical areas at the Trade Desk. And today I'm here to talk a little bit about how we've used Aerospike to solve some of our problems and how we've used Aerospike running on Amazon Web Services to do the same. Just to give you a little bit of background on the Trade Desk, we are an advertising technology company, and we represent ad agencies and advertisers in an ad buying ecosystem. How we do this is, or how this works is, let's say you have Jane, and she opens up a web browser to a major news site, and that site wants to show her an ad. You know, that's how they pay for their journalists. That's how they pay for their revenue. That's where they get their revenue. And what they do is they employ a company called a supply side platform to help them find ads. And so this gives them the ability to source from advertisers all over the world. And what the supply side platform does is they help the national news site find ads that are both lucrative for the site as well as are of appropriate quality and such for them. When that page loads on that site, the supply side platform gets a request that might say, here's a browser, here's their geography, here's the page that they're on, this is the site they're on, and so on. It's very situational kinds of things. The supply side platform will take that information and send that out to demand side platforms like ourselves at the Trade Desk, with that information, and ask them for a bid to show an ad on that spot. When we receive that bid, our job is to look through all the ad agencies' campaigns that we represent and see if there is a match for the criteria given on the request. And there's two dimensions to that. There's situational information, and then there's the context about the browser from other site history. So when we do that, what we look at is an anonymous ID that we get, and we get data from hundreds of different data partners that send data into our platform, so that our ad agencies can use that to help buy the right ads for the right people. We store all of that data in Aerospike because we need a very rapid response, because we get 11 million queries a second coming in asking us to supply bids for ads on the internet. When we get this, and we have very short timeframes to respond to, we try to get it done within 20 milliseconds or less. We have a lot of volume on top of that, and so the problems get very challenging as we go. One of our key partners in this is Aerospike. We've used them for about 10 years. We run some of the largest Aerospike clusters in the world. To us, Aerospike is the best NoSQL solution to support our millions of QPS, and we found it to be just incredibly simple to operate. The dynamic cluster management in that is incredibly key, and we found it to scale quickly whenever we've had challenges in the past. Another partner of ours is Amazon Web Services. We've been a customer of theirs for over 8 years. We run multiple workloads on Amazon. A lot of our log processing, as well as our data warehousing and such, runs on Amazon. And we also run a lot of EMR workloads on that platform. The scalability of this has been really key to our success as well. So we've had some challenges with the fire hose of data. So we're getting, we have a third-party data ecosystem that we support. So we have data partners that sell their data products on our platform. And we have advertising agencies who are trying to use those products to inform their ad buying decisions. We're reading that bid stream at a rate of about 11 million items a second. So we're doing these lookups in our Aerospike caches. Since that is such a high rate of speed, we have to optimize heavily to the read side in the bidding data centers. And so the lookup of information is absolutely key to our business. And so these data centers that we have around the world service real-time traffic from SSPs, and these partners send us requests for bids real-time from all that internet activity we see. The wrinkle to that is that it might not all be in the same region, and so one SSP might have page load in one region that actually comes from another region, and so on. So there's not a perfect affinity between the end browser and where our data centers are, and so on. And since that is true, we have to be able to replicate our data globally so that we can satisfy any request from any given region. The trick about the read-heavy workloads is that we have intense serialization and deserialization costs from the objects that we store in Aerospike. And so we have to be careful of their size, because the larger the size, the more CPU we'll use and consume in processing those requests. And there are about 100 billion records in total, and many with tens of thousands of data points. And so we have to be careful about which data points we select. Again, we're a platform for data. And so you can think of it kind of like a grocery store with shelves. A data partner might say, here's a specific segment or component or list of IDs that identified by, end market for auto, or, somebody who's interested in hiking. And then what happens is we say, we put that on a shelf in our platform, and customers can choose to use this segment or that segment, and so on. And so there's a multitude of things that are used and unused in our platform. Not everybody uses all the segments, and not all segments are in use. So since that's true, we don't want to store all of that in our hot caches inside our data centers that are responding to the bid requests. We also get about 100,000 QPS from data partners all day long, sending us data elements. And it might be one or more segments at a time, depends on the way that they have engineered their systems and their platforms to interop with ours. So in the end, it turns out to be about 30 million ID/segment updates a second, which is a phenomenal volume, and sometimes a bit intimidating. We need to be cognizant of the CPU cost of what we have, of how we do the evaluation of what is in use and what is not. And so what we decided was we needed a new approach to how we looked at things, and that's where we started working on our cold storage solution. So in general, just to kind of recap, data partner will send us data. We receive that data in our data server platform, write to logs or directly to endpoints, including S3. That data then gets, we use SNS and SQS to kind of notify us that an item's in queue. And then we process that data and put it into our cold storage system. Likewise, on the bidding side, we have a similar system that tells us we need to refresh data back out. And so we take the data back out and distribute that to our hot caches globally. The global view is interesting too, because it's a mix of physical data centers and data centers that we run in Amazon. And so in different locations in the EU or in APAC or in the US, we have different varieties of hardware and software implementations that we distribute out to. So it's a complex and non-heterogeneous environment. So we have two basic use cases that go along with this. We have the hot cache use case that I was kind of talking to with looking up an ID and looking up the data that's on that ID. Hopefully that data is only the data we use, because that's all the only thing we need is at the moment. And then we have the cold storage use case, which is initially stored like a key value, just like the other one was. But however, the extracting the data is done on a segment by segment basis. So it's actually the reverse index is what we need to populate all of the use to populate all the data centers around the world. So our original hot caches in some places were a bare metal cluster of 40 nodes or say of specific hardware. We've traditionally used a hybrid approach of indexes in memory, data on SSD. It's due to TTLs and the way that things work in the platform. Sometimes there can be almost 200 billion keys in those platforms. But we use a very much smaller block size for that, because the data we want to manage closely how much data we store on those to reduce our CPU cost overall. So it's very read heavy traffic. It's at each data center you might have 1 million QPS or more. The balance of that is largely read traffic. Write traffic maybe 80% or less. Depending on the day and the point of time. And we've optimized the storage of this with a custom object that we store in Aerospike. It's optimized for our read cases so that we can deserialize it efficiently. It is a very straightforward system where, it's a key value lookup and, but since it is a custom object, we are using a read, update, write pattern for writes. We have to read the object, examine it in code, process it, and then write it back to Aerospike. So when we started moving some of these systems onto Amazon Web Services, we were pretty familiar with hardware implementations and such. And so what we did was we said, let's take a few different kinds of instances. And then we used a tool called the Aerospike certification tool, or ACT. This is critical. The way that they've structured the tool and its ease of use is really a great way to kind of burn in a couple of nodes, a few different instance types, and find the right balance for what you need versus what is available. We found that you have to really run it for more than a day, right? Like you need a good amount of runtime for that so that you can kind of get the wear leveling into the system and understand really how that's going to perform. We ended up settling on the i3EN. They have so much more storage space, but we're a little constrained on memory, but it seems to work pretty well for our workloads. On the hot cache operation side, just a couple of other side notes. We use CloudFormation because we don't want the ASGs to terminate automatically on a node automatically, because we need to be able to bring it down or quiesce it comfortably. We also use Chef extensively to bootstrap and set up the nodes. And one of the trade-offs we found is that it is a little bit slower than the bare metal, but the elasticity gives us far more benefits, and the ability to get to new systems is so much improved. The more interesting use case, I think, of the two is the cold storage use case, in the sense that it is really a bear, and it's a very big platform. The idea is, again, we have to absorb this 30 million tuples a second of data coming in. We need to use that as our store, so that our in data centers can be a little bit leaner on their footprints, and of course more efficient on the processing. It also makes a phenomenal buffer and gives us the ability to operate with a multitude of data partners. And when those data partners, we can free them up from having to worry a lot about flow control and such like that, because we can absorb and buffer the data, and we can make sure that it gets into the platform faster. This case is far lighter on reads. It's even smaller on reads than the write read ratio in their hot caches. But it's a very large data set. So it is about a petabyte of data uncompressed. We've been working on it for a few years. it started out as a Cassandra implementation. We were really intrigued by the ability of Cassandra to absorb large data sets very quickly. And so we engineered a data model and built it up in Cassandra. We built it and were able to absorb the data very quickly in Cassandra. However, the size of the data really did necessitate compression. And it also required, which in Cassandra then also requires a lot of GC if we're getting a lot of rows. And so both of those are very CPU intensive things. And then that really impacted how much density we had for as far as CPU to storage. And so we ended up with this huge cluster of about 500 i3 2XL nodes, which was a little challenging or very challenging to manage at that scale. And we hadn't even really gotten to the read part side of the problem yet. So, and we do have to read. That is a key part of that system. So when we actually went to go implement the read side, we found that the data model wasn't sufficient to really enable us to do the reads that we needed to do. So we started talking to Aerospike, and Aerospike suggested that, a couple of approaches, and we'll go through those in a second. But the real crux of the matter is that the read, we can do stream updates to Aerospike, just like we would with Cassandra, but we can also do reads, and they're just as atomic as they need to be for our use case. And so it was a very excellent fit for what we needed to do. And then, of course, the Amazon EC2 platform solves to let us do the initial point of concept, proof of concept, and let us grow that proof of concept into the full-fledged implementation very easily. So the idea behind the use cases that we're working on with Aerospike is to retrieve. First off, is we have to distribute data out to the edge systems, and that's pretty simple. Primary key read, and we get all the data elements that we need to distribute, and we can decide which ones to send out and which ones to not. The harder use cases are writing IDs to the record. We use map operations on the server so that we don't have to read, update, write. So we can really just submit a request, the data gets absorbed, and we can move on to the next request. And so that helps us do the high volume very quickly. The other part of the read is really scanning through on the reverse index. So coming back through and saying, so out of this population, how do we find every ID that has an attribute that we're looking for? So that we can say that is now in use, and now let's move that out to the hot caches. And so that's a great capability that we found in Aerospike, and it's very helpful. So our initial design, we were calculating out with Aerospike, about replication factor of 2, and then of course room for fragmentation or defragmentation. That came out to about 3 petabytes uncompressed. And then we worked on some optimizations, but still we came down to only about 2.3 petabytes. At which point, working with Aerospike, they implemented compression on their record level so that we could actually get that down to the 1 petabyte that we have today. So we originally started out with about 75 M5D metal nodes using compression. And we found that, with tuning and everything like that, we found that we had to get up to about 100 nodes to be comfortable initially. On the operational side, we found that, in order to store a larger data set in each ID, and of course, this is all the unused data on an ID generally, we found that a 1 megabyte record size was about the sweet spot of where we wanted. But what we found was that writing, since a lot of our updates are small, right, there might be 2K, 3K at most, right, we actually incur a lot of cost because we're writing 1 megabyte records every single time we do an update. So that's something that we're tuning now and trying to understand how to solve a little bit better. That's something to think about. We use the ZSTD compression, and it's been an excellent balance of CPU versus the size of the data on disk. We came out using at about 11,000 cores to drive that Z standard compression. We did stay on replication factor 2 in order to get even more comfortable with that. We found a way to back up onto EBS drives and then to S3. And that has actually proved workable in practice. When we've lost nodes before, we've been able to recover pretty quickly and without any data loss. So the cool thing was about this whole project was that the elastic nature of EC2 got us to full scale pretty quickly, right? And it would let us do a full scale prototype. We were able to distribute data around the world and actually make sure that our problem was actually solved, that we were able to line all the code up with all the concepts and make sure it all worked. It is hard, right? The cluster has grown to 158 nodes, I believe now. And so managing it is challenging, and there's a lot of data moving and a lot of edges that we hit that probably most people don't. The i3 here didn't work out for the cost. We just because the trade-off between the CPU and the disks it was not quite enough CPU to get where we needed for the disk size. So we went with the M5D metals, which allow us to spread out that CPU a little bit better. But we're definitely pushing the disks on those M5D metals. It's been an interesting research project in some cases where we've been, struggling to understand what the limits of the hardware are and so on. A couple of things though, to think about. Lower the RF as far as you can go, the replication factor, because the more crosstalk you have, the more cycles you're going to burn, because you're going to be writing that data on 3 nodes instead of 4 at RF3 or something like that. So be cognizant of that as you go through. But of course, you need it. You need to have more than one node have the data. So obviously it's a judgment call. And also monitor that block size and definitely go as low as you can go. It'll be a lot less stressful on the systems if you can keep that data down to a smaller bit. So in the end, we had some pretty good results. The hot caches that we have in our data centers contain only the data that we need for current ad campaigns. The hot caches are globally refreshed within a short time, even before new campaigns start. When we get data in from data partners, they are now free to send it to us as fast as they can or as quickly as they do. And so our impact on our data centers is negligible now, because now before, when it was just the hot caches, then it would hurt the hot caches. Now we're free from that. Aerospike Spark Connector has also been an interesting tool to be able to use to get insights into the metadata about the data we have, the volumes and the collision rates and so on. And so that's given us a good understanding of what's actually useful in the world, right? As far as like what's available in the bidding stream, what's available in the system, and so on. So it's been a really interesting side effect or thing that we got out of it. A couple of things about lessons learned too. The Aerospike certification tool is absolutely key. You need to run this. You need to understand what the implications are in your systems. It will prove to you what you need. The diversity of instance types that we found on Amazon were super helpful in this case too. And the elasticity gave us that ability to try and to iterate and to see what we could, what would work better than other things. But the key thing I think in this project was the application design opportunities we had in Aerospike were very key in getting us to something that worked very efficiently and has really grown with us for the past few years. All right, so thank you very much for your time. I appreciate your interest, and good luck.